So as I was saying, we're going to try not to. I'm going to try not to go on for too long here today. But I kind of wanted to detail a couple of things admin wise, and then get into some applications of integration. So um, I did finally grade the tests. Sorry that it took so long. You should be able to see your grades. If your grades are not showing up in the grade book for you, I'm not exactly sure why that's happening. It was happening with the quiz. Rest assured that the grades are showing up in my version of the gradebook. They will be computed correctly. Um, However, I'm not entirely sure what's going on the display side of things. So let me know if you're having any issues with that. I'll look into it and make sure that everything is going swimmingly. Um, but as for sort of our plan for the rest of the semester, um, we have, including this class, we have 4 classes remaining. Which is well, technically it's 3 classes and then the class that's supposed to be the final. Normally we would have an exam on the 7th, but since we're doing take-home exams, I figured the final exam will be available after class on the 7th. So that's at about 1:30, depending on when we finish up on that day. And it will be due either on midnight of the 11th or at 2:35 on the 12th. I still am not clear on whether or not I can assign a final exam that is due on the Tuesday, because technically the semester is over on the Monday. Um, I am willing to accept the exams that late, but I just need to make sure that it's not breaking any regulations or anything like that, and I haven't gotten clear word back on that. So I will let you guys know for sure. Regardless, it's more time than I gave you for the last test. Significantly, it's more like 96 hours instead of 72 hours, or instead of like 47 hours or whatever. So it uh, should be a little bit more manageable. Hopefully, you guys can find the time to do that. Um, Unfortunately, I will be basically unable to accept any late work for this one. I basically can't give extensions because grades are due pretty quickly after this, so not a lot of options available. Um, the format of the final exam will be the same as all the rest of our exams. Um, I still have not yet decided if it's going to be cumulative or not. It is likely to not be cumulative, except in the sense that you still need to be able to do derivatives in order to do integrals, right? So it's probably going to focus primarily on integral stuff, but our methods of integration require differentiation. There may be some problems that ask you to sort of filter your way back through things like um, related rates and those sorts of ideas, and view them through an integral. Okay. Any questions about the final exam right now? Um, Obviously, we'll talk more about it.
Is it worth more points than our midterms?
Yes, the final exam is currently worth more points than the midterms, though that was under my. Maybe I will make it cumulative because that was the plan. Generally, was that the final exam was cumulative and worth. Dang it! Because the problem is that if I don't make it cumulative and I want to make it worth the same as the other midterms, then I have to go back and change my syllabus. That seems like a lot of effort.
That's fair.
Yeah. I will give you guys a final decision on that before I give you the exam. Sure. I will give you guys a final decision on that before. How about let's say at next class? I will tell you whether the exam will be either cumulative or not cumulative, and whether or not I'm changing how much it's.
Sounds
Um,
good.
but regarding the last 4 classes, we have some applications of integration that we need to get through. Um, In particular, we're going to talk about average value. We're going to talk about area between curves. We're going to do some applications with regard to work, and we're going to do some applications with regards to differential equations. So that should be able to squeeze pretty nicely into the next 3 classes, which leaves us the Thursday class, the 7th, for review. So tentatively, that's my plan. We'll do applications for the next 3 classes today, Thursday, and next Tuesday, and then next Thursday, the 7th will be a review class. But if there are no other admin questions, we might as well crack straight into it and start talking about applications.
How
So
big is the final gonna be? Oh, so
same
sorry
as
to interrupt
same
you.
as the other tests. 12 questions.
Will there be an extra credit one?
Maybe. It depends on whether or not I can think of a good extra credit problem.
Cool.
Yeah. Yeah, we'll see. So let's
Quick question.
yes.
Will we be receiving a practice final exam?
Oh,
Before?
yes, I can give you guys. I will try to throw together a midterm review sheet by next week sometime.
Sweet, thank you.
All right. With that gotten out of the way, let's talk integration. So just a reminder that part 2 of the fundamental theorem of calculus says that, so let f of x be a function, let f of x, little f of x be functions such that big F prime of x is equal to little f of x. Then the integral from a to b, the definite integral from a to b of f of x dx is equal to big F of b minus big F of a. Actually, let me write one line before that. Big F of x. This bar here means evaluated between x equals a and x equals b. And that represents big F of b minus big F of a. In other words, instead of using Riemann sums or limits of Riemann sums to actually find values by, or find definite integrals by the definition, we can evaluate definite integrals just by anti-differentiation, right? And of course, one of the windows that I closed in my Rampage to try and get rid of the noise was the one that had my notes in it. So give me just 1 second. So, for example, the integral from 0 to 2 of x squared plus 1 dx is equal to, we just need to take an antiderivative here. The antiderivative of x squared is x cubed over 3. The antiderivative of 1 is x. And here we actually don't need a plus c. The only requirement for this fundamental theorem of calculus is that we choose an antiderivative. So we can choose any one we want. We could choose plus 4 if we wanted to, but it's always more convenient to use plus 0 because the plus 4 would just cancel out anyways. So we're going to choose the antiderivative that does not have a constant term in general. And then we're going to evaluate that between x equals 0 and x equals 2. That just means that we're going to plug in 2, and then we're going to plug in 0, and then we're going to subtract them. So we have 2 cubed over 3 plus 2 minus 0 cubed over 3 plus 0, which is 8 over 3 plus 2 minus 0 minus 0, which is 14 over 3. So a lot of the techniques that we're going to look at least the ones we're going to do today, are going to require us to actually do definite intervals. So the first, what I would call, I guess it's kind of an obvious application, is the integral, if this is the function f, right? And maybe this is a and this is b. Well, the integral of f of x is the area underneath this curve between a and b. This area is equal to the integral from a to b of f of x dx. So let's say we had a second function in here. Say we had this function here. And this function we'll call g of x. So the area beneath g of x, why did I do this in blue? I apparently can't color. The area of g of x, we'll call b, is the integral from a to b of g of x dx. That's that area right in here, right? So what's the area between these two curves?
Do we just subtract the two functions from each other?
Yeah, so I mean geometrically we can find the area between the two curves as the yellow area is the black area minus the green area, right? So it's a minus b. In other words, the area between the two curves is, so the area between f of x and g of x is the integral of f of x on a to b dx minus the integral from a to b of g of x dx. There's no particular reason that we have to keep these as two separate integrals. So we typically see the formula that the area between curves is the integral from a to b of f of x minus g of x dx. At least if the curves are expressed as a function of x. Okay. So there are some curves where it's better to instead think of them as functions of y. If we wanted to know the area between these two curves, neither of these curves are necessarily a function of x. This area in the middle, if this was a function of y, and this other curve was also a function of y, then the area here might be the integral from y equals a to y equals b of the larger of the two curves in this situation is the right-hand curve. So that would be g of y minus f of y dy. In this case, we're integrating across the y-axis instead of the x-axis. The only difference between this is that now this is measuring the area between these curves and the y-axis. But that area between the two curves is still the difference of the area between one curve in the y-axis and the area between the other curve in the y-axis. So in general, for functions of x, we'll use that the area is equal to the integral from a to b of top minus bottom dx. And for functions of y, we'll use the area of from a to b of right minus left dy. Technically, if you really wanted to, the order doesn't actually matter, and you can just take the absolute value. If you get the order wrong for one of these problems, probably the thing you did wrong is you switched the two functions. Right? So let's do a quick example. Let's find the area between f of x equals the square root of x and f of x equals x squared. These are two functions that we've seen a lot of, right? Not f of x, g of x equals x squared. These are two functions we've seen a lot of. X squared is, of course, a parabola. And the square root of x is, of course, the square root of x. It's sort of like one branch of a sideways parabola. And we're looking for the area between these two curves. So this one here is f, this one is g. So this we could set up either way. We're already given the functions as functions of x, so it seems reasonable to do top minus bottom. So here we want to do top minus bottom. So our integral will be the integral from a to b of x squared, or sorry, the square root of x minus x squared dx. Now the question is, what is a and what is b here? Well, because these two functions intersect each other at some clear points, it's just going to be the intersection, the two intersections here, this point and this point. So a, b are the intersections. How can we find the intersections? Well, to find the intersections, we'll just set the two functions equal to each other. So x squared is equal to the square root of x. In this case, we should end up with two solutions. If we square both sides, we get that x to the fourth is equal to x, or x is equal to x to the fourth minus, or sorry, 0 is equal to x to the fourth minus 1 minus x, which is x cubed minus 1 times x. And x cubed minus 1 is equal to 0 if x is equal to 1, and x is equal to 0 is our other solution. So we get the two solutions at x equals 1, x equals 0. There's a bunch of ways to skin this particular cat with regards to solving this formula. If you're okay with just saying, well, it's true if it's 0 because the 0 squared is 0 and the square root of 0 is 0, and it's true when it's 1 because 1 squared is 1 and the square root of 1 is 1, then that's totally fine too. This one is not so difficult that you necessarily need to show all of the work in exhaustive detail on finding the intersections. But now that we know our intersections, we can actually set up our integral fully. The integral from 0 to 1 of the square root of x minus x squared dx. And now we can actually compute, right? So we need to do an antiderivative. in order to do this antiderivative, I think we probably want to rewrite the square root of x as x to the power of 1/2 minus x squared dx. We don't have a nice rule for the square root function, but we do have a rule for x to the power of 1/2. We still have our bounds there. The antiderivative of x to the 1/2 is 2/3 x to the 3/2. We increase the power by 1 to get 3/2, and then we divide by the new power. Dividing by 3/2 is the same as multiplying by 2/3. Minus the integral of x squared is x cubed over 3. And we're going between 0 and 1. Here we can plug in our bounds. So we get 2/3 of 1 to the 1/2, 3/2, minus 1 cubed over 3, minus 2/3 of 0 to the 3/2, minus 0 cubed over 3. The whole back part's just going to be 0, and we just end up with 2/3 minus 1/3, which is 1/3. Which ends up being the area between these two functions. So this area in here is 1/3 of a unit, well, square unit actually, whatever the square unit is to be. Any questions about this example? We can certainly do this in other situations as well. Sometimes these get a little bit more difficult, right? So, for example, oops, maybe we get something like let's determine the area between x equals 1/2 y squared minus 3 and y equals x minus 1. So here we actually end up with one function of one x as a function of y and one y as a function of x. So we kind of could go either way, but if we actually take a look at what our graphs look like, it's going to be it should become obvious that we really do want to be looking at right minus left instead of top minus bottom. So that's 1/2 y squared minus 3 and is equal to x, and y equals x minus 1. So here's our two functions. The red function is the quadratic, x equals 1/2 y squared minus 3, and the blue function is the linear function, y is equal to x minus 1. And while there are certainly sections that can be viewed as a top function over a bottom function, there's this bit over here to the left-hand side of the graph where the red function is both the top function and the bottom function. Whereas at every single point along these two graphs, it's really clear that we have a clear left function and a clear right function. So we want to rewrite both as functions of y, then do the integral from a to b of right minus left dy. This means that our bounds are going to be the y coordinates of the intersections, okay? So our bounds are the y coordinates of the intersection. So we want to solve for what y is. We can do that by substituting x in our right-hand equation here. We get that y is equal to 1/2 y squared minus 3 minus 1. Or y is equal to 1/2 y squared minus 4. If we multiply everything by 2 to get rid of fractions, we get 2y is equal to y squared minus 8. So 0 is equal to y squared minus 2y minus 8, which when we factor, we get that y is equal to -4, and y is equal to 2 as our bounds. Sorry, y is equal to +4, and y is equal to -2. The graph bears that out as well. We can see our 2 points of intersections as -1, -2, and 5, 4. So when we set this up, we're going to set this up as the integral from -2 to 4. Our top function is y is equal to x minus 1. So that means that x is equal to y plus 1 when we set it up as a function of y. So that's our right-hand function. So that'll be y plus 1 minus our left-hand function, which is 1/2 of y squared minus 3 dy. This looks like a situation where it might be better to combine some like terms before we take our antiderivative. So we can rewrite this as the integral from -2 to 4 of -1/2 y squared plus y plus 4 dy. And now we can take our antiderivative. The antiderivative of -1/2 y squared is -3/2 y cubed plus 2y. Sorry, plus y squared over 2 plus 4y. And we're evaluating between y equals -2 and y equals 4. So we can plug these in. We get -3 over 2 times 4 cubed plus 4 squared over 2 plus 4 times 4 minus -3 over 2 times -2 cubed minus, plus -2 squared over 2 plus 4 times -2. We can simplify some of these out. We get -3 over 2 times 64 plus 8 plus 16 minus -2 cubed is -8. -8 times -3 is 24. 24 over 2 is 12. -2 squared is 4 over 2 is 2. 4 times negative 2 is 8. So we get negative 64 over 2, sorry, negative 96 plus 8 plus 16 minus 12 minus 2 plus 8. And we get a negative number, which feels like I did something wrong here. Did I do something stupid somewhere that I didn't spot? Oh, I did do something stupid. This is not 3 over 2 y cubed. This is 1/6 y cubed. So this should be 2 over 3. What's 64 over 6? That's 32 over 3? Sure, good enough. And this feels a lot more like a positive number. Yeah. So that gives us our answer of 56 over 3. So in a sense, the tricky part of these problems, once you've set them up, they're almost always easy to set up once you've seen the actual graph. Whether you're graphing that by hand or just knowing what they look like and finding the intersections by hand, or you're actually graphing them using a graphing tool, you can just set them up as either top minus bottom or right minus left. It is important to have an idea of what you're looking at in order to understand how to set up the graphs or how to set up these types of problems. Does anybody have any questions about the 2 examples I just did here? Everyone feels pretty okay about those? All right. The other application that I wanted to run through today is the average value application. And this also has to do with we're coming back around to a mean value theorem again. This one is the mean value theorem for integrals. So first, if we have some function of x, so let's say this is f of x, if we know the area of that function, so if we find the area of this function, then if we were to find a rectangle with the same width and area, then the height of that rectangle should be exactly the average value that f of x takes on that interval. So the area of that rectangle would be, so if this is from A to B, the area of that rectangle would be B minus A times the average value, which we'll call B. And the area beneath f of x is the integral from A to B of f of x dx. So what we get is we get our formula for average value. The average value of an integrable function f of x equal f of x on the interval a to b is f average is equal to 1 over b minus a. That's the width of the interval times the integral from a to b of f of x dx. So I haven't actually defined the term integrable, but it should be a pretty obvious term. Integrable means that you can take the integral. It turns out that integrable is actually a pretty loose thing. If you're just talking about Riemann integrable, then actually you don't need that your function be continuous. You need that your function be defined everywhere, but it can be very badly discontinuous. It can actually even be infinitely discontinuous as long as it's not uncountably discontinuous, which is sort of a weird distinction. For example, I think early on in the semester we chatted a little bit about the Dirichlet function. The Dirichlet function fails to be integrable because it has a discontinuity at every single irrational number, and there are an uncountable amount of irrational numbers. But for example, the step function over any interval is like the greatest integer function or the floor function. That function is totally integrable. It makes a lot of sense that it's integrable. In fact, it's very easy to find the integral of because computing the value beneath those curves is incredibly simple, right? You're just taking the area of the rectangles. All of those areas are just rectangles. But side notes about integrability aside, let's go ahead and do an example of this average value formula. Let's find the average value of f of x equals x squared minus 5x plus 6 cosine of pi x on the interval from -1 to 5 over 2. So we're just going to apply the average value formula. F average is going to be 1 over 5 over 2 minus -1 times the integral from -1 to 5 halves of x squared minus 5x plus 6 cosine of pi x dx. This integral here is slightly trickier than the previous integrals that we've done. Very, 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 very slightly. Notice first, 1 over 5 halves minus -1 is 1 over 7 halves, which is 2 over 7 times the integral from -1 to 5 halves of x squared minus 5x. I'm going to split this into two integrals because we need a u substitution for this part back here. The cosine of pi x is something that we're going to have to use a small u substitution to deal with. So this left-hand integral is pretty easy to deal with. So it'll be 2/7 of, this will be, so the integral of x squared is x cubed over 3. The integral of 5x is 5x squared over 2. And this is just evaluated between -1 and 5 halves. the integral of cosine of pi x is a little bit trickier. So let's go ahead and box ourselves off a little bit of scratch work over here. The integral of cosine of pi x dx, we're going to choose a u substitution for this. U equals pi x. If u is equal to pi x, then du over dx is equal to pi, which means that du is equal to pi dx, which means that dx is equal to 1 over pi du. So the integral of cosine of pi x can be rewritten as cosine of u times 1 over pi dx. So du, sorry. So our integral here ends up being cosine of u over pi plus a constant, or cosine of pi x over pi plus c. So we can fill this result in. We get 6 times cosine of pi x over pi. And this is I feel very bad for my poor tablet. I don't think it was ever really meant to do as much as I've been doing with it lately. And this is evaluated between -1 and 5/2. This one we probably want to plug into a calculator straight away. So we have 2 over 7 times, first we'll plug in 5/2, so that'll be 5 over 2 cubed divided by 3 minus 5 times 5 over 2 squared over 2. Put all of this in parentheses, and we'll subtract. Same thing, but with a -1 inside instead. So that's what I just typed in there, that's this first part here. Now we need our other part, so that'll be +6 times cosine of pi x, pi times 5 over 2. Boy, it really doesn't want to do this nicely. I'm in degrees for some reason. Divided by pi. Just 1 pi. Minus this guy again, but this time instead of 5 pi over 2, it'll be -pi. And I think that should do it. Let me just make sure that everything is plugged in correctly here. Yeah, we have 2/7 of that whole thing, and our answer should be about -0.371. Oh. Again, I'm very stupid. I did all that work here, and I never did the integral. So the integral of cosine is not cosine. Integral of cosine is sine. So these should be sines instead. And that gives us the exact same answer, which it shouldn't, which means I probably plugged something in wrong. So maybe we should do this in smaller parts. Let's try 2/7. So to rewrite this a little bit more simply, we should have 2/7 times x cubed over 3 minus 5/2 x squared plus 6/pi sine of pi x and that is evaluated between -1 and 5/2. So let's try just evaluating it at 5/2 first. So that's 1/3 times 5/2 cubed minus 5/2 times 5/2 squared plus 6/pi times sine of pi times 5/2. So that's our first part of the integral, and then we'll do the same thing. We'll do 1/3 times -1 cubed minus 5/2 times -1 squared plus 6/pi times sine of -pi, which is 2.83333. And then we'll do this one minus this one. And then we'll multiply that whole thing by 2/7 to get the actual correct answer of approximately 1.621. So one of the lessons to take away from this is that evaluating integrals can actually be really, really messy. There's a lot of plugging in, a lot more plugging in than we've seen in evaluating things in the past, because every single time you have to plug something in, you actually have to plug it in twice. Okay, so what I did the second time is probably a better model for how you should consider plugging things in. Plug in small chunks and then keep as much information as you can to combine those chunks together, rather than trying to say just plug in everything all at once in one. It's likely that you'll make a small mistake somewhere, which I definitely did. I'm not exactly sure where I did it, but I definitely made a small mistake in there somewhere, and it led to having a wrong answer. So the last thing I want to speak to before letting you guys go is the average value formula yields something called the mean value theorem for integrals. and it's very similar to the original mean value theorem in application, but it's a little bit almost easier to sort of write. It says that if f of x is a continuous function on a to b, then there is a number c inside the integral, or the interval from a to b, such that the integral, c is equal to 1 over b minus a times the integral from a to b of f of x dx. That is a continuous function on an interval must achieve its average value on that interval. This is pretty similar to the mean value theorem for derivatives, but instead of giving an average, like saying that given a instantaneous, or given an average rate of change over an interval, it must achieve its instantaneous rate of change somewhere on that interval. This one says that if a function has to actually achieve its average value on that interval. Okay, I'm sorry, I shouldn't have said c, I should have said f of c is equal to 1 over b minus a times the integral from b to a of f of x dx. So this is another one of those sort of application things, or this is a it's a theorem, right? So the fact that it guarantees it doesn't necessarily mean that you're able to find it, but you can often find it, right? For instance, find, as an example, find the value c that satisfies the integral MVT for f of x equals x squared plus 3x plus 2 on 1 to 4. So first off, notice that this function is continuous. And we do have this closed domain, so the MVT does apply. So we need to find our average value. F average is the integral from 1 to 4, or sorry, is equal to 1 over 4 minus 1 times the integral from 1 to 4 of x squared plus 3x plus 2, which is equal to 1/3 of the integral, or 1/3 of x cubed over 3 plus 3x squared over 2 plus 2x evaluated between 1 and 4, which will be 1/3 of 4 cubed over 3 plus 3 times 4 squared over 2 plus 2 times 4 minus 1/3 of 1 cubed over 3 plus 3 times 1 squared over 2 plus 2 times 1. So the first one is 4 cubed over 3 plus 3 times 4 squared over 2 plus 2 times 4. And the second one is negative is, sorry, 1 over 3 plus 3 over 2 plus 2. And we'll do 1/3 of the first one. I just realized that you guys can't see the calculator entirely. Minus the second one. To get 16.5 or 33 over 2. So our average value is 33 over 2, so we want to find C such that f of C is equal to 33 over 2. Well, that means that 33 over 2 is equal to x squared plus 3x plus 2, which means that 33 is equal to 2x squared plus 6x plus 2, which means that 0 is equal to 2x squared plus 6x minus 31. And from here, all that has to be done is to use the quadratic formula, actually, right? So that would be C is equal to -6 plus or minus the square root of 6 squared minus 4 times 2 times -31, all divided by 4. So that would be -6 plus the square root of 6 squared minus 4 times 2 times -31, all divided by 4, which gives us our value of, so technically we do get 2 solutions, right, for this quadratic. But only one of them is actually on our interval. Go ahead.
When we multiplied by 2 both sides, did we miss the +2 at the end?
We did miss the +2, thank you. So that should be a 4, so this should be a 29. So this should be a 29. And this should be a 29. Thank you, Isaiah.
Yep.
So we get approximately 2.6 or 2.593 as our answer instead. We can still throw out this other one, this -5.61, because we know that our root has to be a positive root, right? It has to be between 1 and 4, and only one of these is between 1 and 4. So the value we're looking for is C equals 2.59.
Cool,
All right.
cool.
Does anybody have any questions about these two applications? They're about as straightforward as we can possibly make these applications. You're just applying exactly the definition of integration as an area, right? So when we're applying these, we're just finding these areas, or in the case of the average value formula, we're taking that area and finding the average height on the area. All right. I think that will do it then for today. I will post some problems for you guys to go through. Crap. I think I mentioned on a lot of different tests that I think 9C was a weird problem and that we would go over it in class. I'll go over it at the class at the beginning of next class. It is a little bit tricky, and I kind of screwed it up, so I was pretty generous with points on that problem if you didn't quite get the answer right. So hopefully there shouldn't be anything too weird about that.
Which one was that? 5C, you said?
And 9C, I think. The x to the power. It was okay. Let's just talk about it right now. So it's the limit as x approaches 0 of x to the power of 1 over x. This is something that you can. Well, so first off, this limit doesn't exist. It doesn't exist because x to the power of 1 over x is undefined for x less than 0. If you have a negative value of x, then a negative number to a fractional exponent, it's not well defined. It can be well defined for very, 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 very specific values. Like -3 to the -1/3 is well defined. But the problem is that a lot of these fractional values are totally not defined. So like if you actually graph this function, if you actually graph x to the power of 1 over x, you get, so undefined is probably incorrect for me to have said. You may have noticed that a bunch of spots appeared over here because there are specific spots where it is well defined. But for the most part, it's mostly undefined over here, right? It's totally undefined if x is irrational. So there's nowhere to approach on the left-hand side. The right-hand side does approach 0. So actually, Desmos is even saying that the value is actually 0. We can do this, so we can find the limit as x approaches 0 from numbers bigger than 0 of x to the 1 over x using L'Hopital's rule. And what we can do is we can say, okay, let's apply a logarithm to x to the power of 1 over x, right? So for instance, we might say that y is equal to this limit. So we can apply a logarithm to both sides to get that the natural log of y is equal to the limit as x approaches 0 from above of the natural log of x to the 1 over x. And then we get the limit as x approaches 0 from above of ln of x over 1 over x, or ln of x over x. And this you can use L'Hopital's rule on. But again, anyone who said that the limit was 0 was technically incorrect because the limit doesn't exist at all. And most of the people who said the limit doesn't exist didn't justify it correctly, which again, my intention was for this exact thing to happen, for you guys to apply L'Hopital's rule and to get 0 as your value. However, I typoed and I accidentally gave you the limit as x approaches 0 rather than the x approaches 0 from above. So I tried to be pretty generous with partial credit on it. There are comments on your guys' tests. They're not actually on the tests. They're sort of next to the tests in the, like I have a little notes box. So I tried to give some comments. If you have any questions, as usual, feel free to reach out to me and I'm happy to explain my thoughts a little bit more in depth. But otherwise, yeah, that's the only question that I really wanted to talk about. So this was 9C on the test.
One last question.
Yes.
The review exam, when did you say that you should have that out?
Eventually. So I'll try to get it up by Tuesday of next week, so that you'll have a
Sounds
chance to
good.
look at it before Thursday when we do a review.
Sounds good.
Any other questions before I let you guys go?
Yeah, can we get an answer key with the review test too, so we can
No.
self-grade?
No. It is unlikely that I will have an answer key for the review. So, I don't love handing out answer keys with things because I've found that what ends up happening is students just end up copying the answer key and not actually getting anything out of it. That's debatable as to whether it's true or not, but nevertheless, I don't love doing that. As usual, I will be available to answer any questions. If you want to check your work, you can ask me to check the problem. A lot of the problems can also be checked through other means. For instance, any integral problem can be checked by doing the derivative of your result. If the derivative of your result is the thing you soldered with without constants or whatever, then you did the correct thing. Any other questions? All right, I will post some problems and let you guys go for now. And I will see you guys on Thursday.
Thank you, Aaron.